Yes, I'm a statistician, which means that I'm not an engineer, but I'm a kind of uncertainty engineer in ways that I won't go into in too much detail, but uncertainty and variability are the entire focus of my professional career. So hopefully I know a bit about them and try and convey some of it to you. So one of the areas I'm particularly interested in is uncertainty in the predictions of complex mechanistic models, which I call simulators. So we use these things in almost every field of science, technology, etc., and they use it for various purposes. A lot of people use these models not to predict anything, but just to see what happens when you write these equations down and compute the results. They use it to try and understand processes in a sort of hypothetical way. But when these models get moved into the area of being used for prediction or control or some real decision making, then they matter rather more. They're usually implemented in computer programs, of course, and these are often computing really heavy codes. They take minutes, hours, days, even months to compute a single answer. Anyway, we'll call them, just as I say, simulators generally. And there's a growing realization from people who are using them to make actual decisions, make real predictions, that it's rather important to know how accurate they are, know what the uncertainty is in these. And that's what this whole meeting is about. There is no point in running a program and getting an answer that you know is not accurate, you know will have some inaccuracies, uncertainties associated with it, and then not try to quantify those. The person you're giving the answer to doesn't know what to make of what you've given them. Is it plus or minus 10%? Is it plus or minus 110%? Until you tell them, they don't know what to make use of it. And it makes it very easy for them to dismiss what you've done, not take it seriously. You will get taken seriously when you're able to say how accurate your answers are, and to be able to back that up with demonstration of the appropriate theory that's done that calculation. So, come on, do something. How do we get it to move on when this thing doesn't work? Okay. Some examples, much wider range of examples that I'm interested in than the ones you've been describing, but here's some. Climate prediction. Many processes involved in these things. Oh, come on, don't do that. Many processes involved, and a really complex climate model will have all these sorts of things in, things like volcanoes and the effects of vegetation and so on. That's a really bad picture of molecular dynamics, but molecular dynamics models are very big and complex because they have many molecules that they're trying to measure the interactions for. All the interactions between them are behaving in relatively simple ways, but there's just a huge number of them interacting. Nuclear waste disposal. Models that describe what happens when you try and bury nuclear waste underground. Here's your containment facility here. You're going to shove the stuff down there, seal it up, and leave it to do its thing and decay nicely over however many thousands of years it needs to do. And the model's going to say, well, what's going to happen when we do this? How long will the stuff stay in the containment vessel? Because this is going to decay, it's going to rot in some way. The stuff will get out, it'll get into the groundwater. How fast will that be conveying it up to the surface, etc., etc. And models of this sort of thing even include things like 2,000 years down the line, humanity is degraded down to subsistence farming. How much are they going to get from their crops being contaminated and so on? Big complicated models. Oil fields, not a nice picture, but a similar sort of thing. It's all about the geology, although you're using it in different ways. And these models can be very big and take a long time to run. A model that simulates an oil field as you put different extraction and injection facilities in may take a day and a half to do one run. Here's your engineering design. Hydrology, something similar. Now, I do this to show you the range of sort of models that people have been building, and that they've all been interested in the sort of questions you've been asking. Some more than others. You're actually behind some of those fields in terms of how much awareness and how much work has been put into doing these things. So you're not going to get all your answers by staying within your one field. You'll just be reinventing things, and probably not very fast, that are already available elsewhere. You need to look wider. The project I've been involved in has been trying to talk to all of these communities to understand what they can do. Okay, let's do some, am I the first one to put an equation up? I can't remember. Anyway, a simulator is a very simple equation. A simulator takes inputs x and produces outputs y. Okay, so the simulator is a function, all right? And that function I'm going to call f. So we take this big, complicated computer model and we call it f, all right? And that's not trivializing it. It's a very complicated function, but it is just a function. Okay, the question is, when I do this thing and I put x in and I get y out, how might y differ from the true thing I'm trying to predict? The real world z. Well, it might differ because I get the x's wrong. I have errors in my inputs. And I talk about inputs in a very general sense. They can be initial values, forcing inputs, model parameters, anything that you either have to put into the model or which is already built into the model but is uncertain. So many models include equations with parameters in them that have been determined empirically. They're best estimates, but nobody actually allows you to tweak those. But in principle, those ought to be tweakable because they are part of the uncertainty in that model. Okay? But if you can't tweak them, after you've tweaked all, after you've put in the best possible values of all the x's and you've got those right, still y won't be equal to z because all models are wrong. There's errors in the model structure and there's errors in the model solution. We've actually heard about the model solution a little bit today. So there are solution errors, there are bugs in codes. All codes have bugs in them somewhere. You hope that all the ones that matter have been removed, but you don't know for sure. But all models have wrong, inaccurate or incomplete science. There are always things that you haven't put in there. So your model assumes that this material is uniform, homogeneous, and it isn't. Of course it isn't. Okay? I mean, I remember when I was doing applied maths at school, we had these inextensible strings, you remember? With no diameters to them and things like that. Okay, well, that's going on all the time in the models, okay? To a greater or lesser extent. So all models are wrong, and therefore they don't predict reality accurately. Not perfectly, at any rate. So we need to quantify these uncertainties. And again, because uncertainty is my whole stock in trade, I don't want to miss any of those uncertainties. I want to find all of them when I'm looking for it. It makes it very unpopular. When you go to somebody and say, you've missed a source of uncertainty, you actually should be more uncertain than you think you are. Okay? But we want to provide a probability distribution, because that's the correct way to describe uncertainties. A probability distribution for Z, the real world value. And this distribution will be centered on some best estimate, and it'll have a spread which shows how uncertain we are around that best estimate. And the fact is that because it's a distribution, it will at least acknowledge we don't know Z. Okay? So how do we get that distribution? Well, part of the story is to characterize your uncertainty about the inputs X. Get a probability distribution on those. That's what Louise's talk was about. And many, many quite sophisticated ways that we might want to try and do that, where she described a couple of those. Propagate that through your model to get a distribution for Y. A Monte Carlo sampling has been mentioned. Monte Carlo sampling involves generating a random sample of X values. I think it was Dietmar's presentation described this very nicely and simply. Generate random samples of X values, run the model for each one, get a random sample of outputs, and that's sample from the distribution PY that you want. So if you could do this enough, and you could do many, many, many random samples like this, you will construct a picture of that output distribution that's as accurate as you want it to be. Problem is, of course, it might take you an awful lot of computing to do that, but in principle, Monte Carlo will do what you want. And if it will do what you want, it's probably the easiest and best way to do it. Simple enough, do it that way. Okay, what about the structural uncertainty? We need to try and characterize our uncertainty about the difference between Z, the reality, and Y, which is what you get when you run your model with the best or true values of X. That's harder. Okay. I gave a talk to this, a title to this talk of Quantifying and Managing Uncertainty. One step is to say how much uncertainty you've got. But people actually often want to go further than that. They want to say, well, where's that uncertainty coming from? Which are the main sources of this uncertainty? And how can I reduce the uncertainty by targeting those sources? So to reduce uncertainty, the basic answer is you've got to do better. You've got to get more knowledge, information into the system. Now you can do this in an informal way. That's to say, you can informally describe the consequences of knowing more. So you say, I now know more about X. I think I've got better estimates of my inputs. I'm less unsure about them, so I'm going to tighten that distribution on the X's. And when I propagate that through, I'll get a tighter distribution on Y. Or if you've done better modeling, better programming, whatever, so that your structural uncertainties are reduced, then again you could say, I think my structural error will be smaller, I'm going to put a smaller and tighter distribution on it. So you could do that informally by simply changing those components. But it's better to do this thing properly and to do it scientifically so that you can justify it to other people and indeed to yourself. So we can use data. That's very important, using real-world data, test data. We can use that to calibrate, learn about the model parameters, and formally reduce our uncertainty. This is not how most people do calibration. Most people do calibration by finding best fit and then pretending they don't have any uncertainty anymore. It's a very bad idea. Okay, but proper calibration reduces uncertainty about model parameters. There's this thing called data assimilation, which is a similar sort of thing in a dynamic model. You dynamically learn about the state variables to try and keep your simulation on track. You can learn about structural error, of course you can, because you're observing Z, you're observing the real world. And by seeing how close you can get to Z by calibrating and then looking at the calibrated model, you'll be able to learn something about structural error. And of course, at the end of all of this, you want to validate what you're doing with real-world data. So all of this process is part of managing and understanding uncertainty. And I think it goes rather beyond what we've talked about today, but in a sense that's the next stage that you need to do after you know how to do some of those other things as well. Okay, so far so good. We've talked about sort of the principles of these things, but in practice there are many technical difficulties in doing this. Formulating the uncertainty on the inputs is an important process, and although it wasn't mentioned by Louise, very often we need to just ask the experts, at least about some aspects of those uncertainties, because we often don't have data or knowledge that is well defined to tell us about the uncertainties of some of those inputs. And elicitation of expert judgments is another area that is a research interest of mine. It's a challenging area in its own right. Propagating the uncertainty, of course, is another issue, because Monte Carlo may be a great way of doing it, but it can be quite slow. And then modelling the structural error is a huge challenge, and I can't say I know too much about how to do that, but we're making a start on that in the team I work with. And anything involving observational data is going to be messy, because we're now talking about the real world. The real world's always going to be more messy than the imaginary world you've made up with your model. Okay? It's going to behave less nicely. And computation, after all of this, is the major challenge that I'm particularly interested in here. Because when we're running big models and we're needing to run that simulator many times, tasks such as this uncertainty propagation, I say you typically need thousands of simulator runs. We've seen things talked about with hundreds or 1,000 to get a really good idea of what's going on, particularly with multivariate outputs, and to be able to characterize the distribution accurately. You do typically need thousands of runs. And if you want to actually delve into that uncertainty anymore and look at sensitivity analysis, you may need many more thousands of runs. Calibration is another process which requires lots of runs of the simulator. When you're trying to search through a high-dimensional space of possible input values to find values that actually fit the observational data reasonably well, that can be a very intensive process in itself. So all of this is impractical if the simulator takes more than a few seconds to run, or unless you've got a very, very large array to work with of CPUs. Even if you can do it with Monte Carlo or with these crude techniques, being able to do it faster is going to save you time, more efficiently. It's going to save you time, and also means that you can tackle bigger problems. And the truth is that no matter how much our computing power increases, the modelers will keep pace with that in terms of the complexity of the models they create. I never knew a modeler who didn't know what he would do with his next grant. Okay? He knows what he wants to put into his model next, which is another reason why we know they're all wrong. Okay? He will try and pretend it's good now, but if you gave him another million, he could do better. Okay? So, we're always pushing the envelope with our computational power. Even though we get the computing power up and up and up, the models go up and up and up to follow it. So being efficient in these things it has a payoff all the way down the line. So the thing I'm going to be talking about is the Gaussian process emulator. I'm not going to describe what the Gaussian process is. That's getting too technical. All I'm going to give you is a sort of a flavor of how this thing works. This was first early work in the 1980s before I got involved with it. What you do is you consider the simulator, f, as an unknown function. Now, in principle, it's a known function. It's a well-defined function. It's a set of equations that you're solving. But the truth is that until you actually run it, you don't know the value for any x. So it's unknown in that sense. So we're going to call it an unknown function. So it's got uncertainty. So it's going to be, in statistical terms, a random process. A random process is a random variable that has an argument, often time, but it doesn't have to be time. It can be, in this case, all the inputs to the simulator. So we represent it as a random process, and the Gaussian process is the particular kind of random process that we use. It happens to be very convenient for what we do. It happens to be very flexible, and we use it for the same sort of reasons that statisticians use Gaussian distributions everywhere, and all sorts of other people do. They're very convenient and well behaved. Of course, there's a price you pay for doing that, but it's actually quite a small price in this problem. The Gaussianity, normality part of it, is actually quite a small assumption. Okay, a Gaussian process, technically it's conditional on some hyperparameters, and we may have a thing called a Bayes linear analog of it, but essentially the Gaussian process is the tool we use. So, we run a number of training runs of the simulator at various x values. These are designed in some way. In fact, so-called maximin Latin hypercube is a very favorite type of design to use. It's not just any old Latin hypercube. We generate very many Latin hypercubes and choose the one which is best spacing its points around the design space. So we maximize the minimum distance between any 2 points. That's the maximin Latin hypercube. That's just one of the designs that's used. So we take a sample of these x values, and they're not random x values like in Monte Carlo. That's one reason why Monte Carlo is inefficient. And then we condition the Gaussian process on those data. What we're doing formally is we're saying, I have an unknown function. but I know it goes through this point and this point and this point and this point. Okay, and that conditioning, in a fully probabilistic sense, is saying what's the distribution of f given that it goes through those points. That's what we do. And as I'll say again, but probably, it typically takes far fewer runs than Monte Carlo. Our best result is sort of 3 orders of magnitude, 1,000 times fewer runs than we needed with Monte Carlo to achieve the same accuracy. Okay. So this is what we call an emulator. What is an emulator? Well, it is the posterior distribution of the simulator. We're using Bayesian statistics here because, well, for various reasons, but you really need Bayesian statistics to talk about a distribution for a function of this kind anyway. But we take a prior Gaussian process, we train it, we condition it on the data, we learn about the parameters within the Gaussian process that we call hyperparameters, and the result of all of that is the posterior distribution. It's a probability distribution for the simulator based on the data we've got. That's called the emulator. Now this is a complicated thing because it's a whole big fancy complicated probability distribution. It's probability distribution for a whole function. But for instance, the mean of that distribution at each point x is a function. That's our best estimator of what the simulator would produce at any given x. It's a predictor. You could think of this as a simple surrogate model. Okay? But more than the mean function, we have uncertainty around that mean at every x. We know how accurate our emulator is at predicting the simulator. Okay? I'm not here concerned with the difference between simulator and reality. I'm not concerned with that structural error at all. In fact, I'm not even here dealing with errors in the x's. The uncertainty I'm talking about is what we call code uncertainty, which is given that I have only run this thing at a finite number of points, and I haven't in particular run it at the x I'm interested in, I'm uncertain about that x. And that uncertainty is what we call code uncertainty, what the emulator actually quantifies within itself. And here's a point here, it correctly reproduces the training data. This is something that nothing else in the field does. No other surrogate does this with an appropriate description of uncertainty. So let me quickly show you what that is. Let's suppose I've got a very, very simple problem. I've got one input x, and I've got one output y. Okay? I've run the simulator twice. I've run it at x equals 1 and got that value. I've run it x equals 5, and I've got that value. The circle is just to mark the spot. Its width has no bearing. It's not saying I'm uncertain about anything there. It's just marking the spot. Okay? So I've done these 2 runs. After I've done that, what have I got? Well, my simulator, I've only known these 2 points for it. What will happen at x equals 3? I don't know, so I'm uncertain. The emulator mean is this straight line here. Well, you can put a straight line between 2 points. That's fine. The uncertainty around it is shown by these dashed lines, which are plus or minus 2 standard deviations, and show that, for instance, at these points, not only does the mean go through the point, but my uncertainty comes to 0. The emulator correctly reproduces what I know. If I run this simulator again at x equals 5, I will get the same answer. It's a deterministic simulator. So I know that. I don't know what it will do at 3. My best guess is it's halfway between the 1 and the 5, but with this much uncertainty. If I now get another point, and now actually run it at x equals 3, and I find it's here, okay, it's no longer on the straight line. My mean function of my emulator now is a smooth interpolator of those points. It's actually a radial basis function interpolator. But my uncertainty has been reduced. What happens is I now pass through this point, but I also can pinch my uncertainty down to 0 at that point. I know what happens there. And as I squeeze my uncertainty down at that point, it obviously must go down in between. If I get a couple more points, and I pinch that uncertainty in at those points as well, I find that now I'm pretty sure what's going to happen all the way between 1 and 5. Now you may say to me, well, how can you know that? This thing could do this. couldn't it? Well, it could. In principle, it could. And what I'm saying here is these are 95% bounds. That thing is included as a possibility. It's just a very small possibility. Why is it very small? Well, if it was doing that, how unlucky would I have to be to get 5 points that look like this? That's what statistics is all about. It's saying, if that's the truth, what's the likelihood I would get those data? The chance of me getting nice smooth data when the function is smooth is much higher than when the function is rough. So smooth data suggests to me a smooth function, and so I give a very low probability to anything lying outside these nice bounds here. That's what an emulator does. That's a very simple example. Of course, I need to work in many more dimensions with many more points, but the same basic idea applies. Given enough training data points, even with a relatively large number of inputs, I can emulate the simulator as accurately as I need by just pinching at every point in that space where I've run it until the posterior variance is small everywhere. Now, there's a lot more going on here. There's an underlying variance parameter that I'm actually learning from the data as well. So if I get data that are very variable, then I will have bigger bounds, and so on. But I can do this in principle, even in quite complicated problems. And typically we find we could do it with orders of magnitude fewer simulator runs than traditional methods. Remember, we have a measure of how accurate we are. Monte Carlo has a measure of how accurate it is as well. It comes from how much variability it finds when it randomly samples. And we can compare the two methods, and that's why I say we can often do so much better, because we can say with these many runs we've got a figure to this accuracy for whatever we're interested in. And I'll show you various things we might be interested in later. And Monte Carlo gets the same accuracy with many, many more runs. We use the emulator to make inference about anything else we're interested in. We do it once. The thing about Monte Carlo and other such techniques is you typically have to rebuild it and rerun it for every different question you want to ask, because it needs a different kind of simulation. We do one set of runs, build the emulator, and then we use it to make inference about all the other things we're interested in. When I say inference, that's what we're doing, statistical inference. So I'm estimating the function, I'm estimating it with some uncertainty. I can do uncertainty analysis. That's saying how much uncertainty is there in Y given I'm unsure about X. Mentioned by other speakers here today, or equivalent ideas. Well, I can do sensitivity analysis. Louise, in fact, mentioned sensitivity analysis using derivatives. That's called local sensitivity analysis. I don't like it much. I much prefer global sensitivity analysis. We heard about correlations, in fact rank correlations, which is actually quite a good global sensitivity measure. I'll show you a different one shortly. But we can do all kinds of sensitivity analysis. We can compute all those things from one emulator. I can do calibration, data assimilation, validation. These all require me to start talking about the real world and start modeling the difference between the simulator and the real world, which is a whole other part of the package. But the emulator does the simulator part for me, and will, again, only need doing once. I can do optimization. Anything you want to do with your simulator, I can do with the emulator, and also say how accurately I am getting the answer I would have got if I'd been able to do it with a simulator, if I'd been able to make all those runs. Okay. Here's a quick example to show you some of the sort of outputs we get and the complexity of the problems we tackle. This is a simulator which models growth of vegetation and carbon exchange as vegetation grows. So as vegetation grows, it, through photosynthesis, takes carbon out of the atmosphere in order to, from the carbon dioxide, in order to use that carbon to build plant material. It gives off the oxygen, of course, that it doesn't need from the CO2. But then, of course, it also respires overnight, so actually gives out carbon dioxide, and the leaves fall off, they go into the ground, they decay, more carbon dioxide is given off, etc. So this whole process is modeled in here with the question, do our forests actually net take carbon out of the atmosphere when we allow for all of these processes? And the answer is it depends upon lots of things. It depends upon how the plants behave, the properties of the different types of vegetation. It depends upon how soils behave, and it also depends upon the weather. In a good year, we might grow a lot, take a lot of carbon out. In a bad year, we might not. So what we did was we ran this model in order to estimate how much carbon was taken out of the atmosphere by all the vegetation in England and Wales in the year 2000, using all the weather data we had for that. And we ended up with this estimate, 7.61 megatons of carbon, plus or minus a standard deviation of 0.6. The standard deviation reflects uncertainties in these things, but it doesn't reflect uncertainty about the model. There's no structural uncertainty in that, and it's probably quite large. So this is only a partial analysis, but as far as we've done, it's what we could do. It's been updated a little bit to include uncertainty about ground cover, about what kinds of vegetation exist at different places. Okay, and so we can produce maps that say, the negative numbers here for the mean are places where we are actually giving off carbon. So in the industrial heartland and so on, we're actually not absorbing carbon. There actually isn't much vegetation there to do it. But in all these places where we've got forests and we've got peat bogs and things like that, historically there's been a lot of carbon sequestration from the atmosphere, and we'll continue to do it. At least in 2000 we appear to have done, with these standard deviations on here. The black spots are points at which we've done more intensive analysis. The rest is interpolated between with another kind of emulator. And at the end of the day, again, quick analysis. Here's our 7.61 megatons. Estimated 4.6 of that comes from grasses. Only 1.69 from deciduous forests and 0.78 from evergreen trees. So there's a lot of uncertainty in these figures as well, particularly in the grasses, because the model wasn't originally designed to describe grasses. There's our 7.61. This is a sensitivity analysis. This is saying how much of the variance is due to different things. So this is a variance-based sensitivity analysis. It's a global analysis. And there's another part here which we can allow for other kinds of uncertainties. And the variances can also be decomposed into main effects and interactions and so on. I just want to point out this other column here, the plug-in estimate. This is what happens when you put in your best estimates of all the inputs. And you simply run the model once. Run the model once, you get 9 megatons. Remember our standard deviation is 0.6? That makes that about 4 standard okay. Somebody take 9.06 minus 7.61 divided by 0.61. It's about 2.5 standard deviations away, or something like that. Anyway, this is outside what you'd think was a credible bound based around this. Why is that happening? Because their best estimates for how these, what these parameters should be, basically make the plants grow as well as they could do. They think that, well, you know, they ought to have evolved into optimal behavior. Actually, they clearly, when you allow for uncertainty about those things, they don't. And overall, wherever you perturb away from those conditions, you tend to go downwards. And if you hadn't done this analysis, they would never have known that. A lot more comes out from this as you go along. Their model was rebuilt 3 times before we got to here, because every time we tried to do this analysis and tried perturbing the inputs, we found that it behaved in very strange ways, or it would crash. Have you found that yourselves? Yeah? It's a very common thing. Modelers don't do this sort of thing, and when you do it, they quite often say, that's interesting, I'll come back to you when I've fixed that. Okay. The role of emulation in this particular example, Gaussian process emulation, was crucial, but we simply couldn't have done this otherwise. It takes about 3,000 simulator runs just to get one output, because you're running it at over 700 locations, pixels, in England and Wales. So each one of those is a separate run. Plus, you're actually running for 4 different kinds of vegetation at each pixel. So it's essentially 3,000 simulator runs. So although each one's quite fast, we're only talking second or two. 3,000 of them is already taking a reasonable amount of time. Now you want to account for uncertainty on that. Imagine repeating that hundreds or thousands of times in Monte Carlo, and then having to do that again to calculate the sensitivity for each different input group. You'd really very rapidly run out of time. So we emulated each plant functional type, those 4 types of vegetation, at a sample of 33 sites, those spots. So at 33 sites, 4 plant functional types, we did do hundreds of runs. And in each case, built an emulator for the behavior of the output at that time. There's a fair amount of data reduction going on here. There's which inputs can we ignore, etc., etc. But then we did that, and typically we could do it with only a couple of hundred simulator runs for each. 1 or 2 of them took more. We then interpolated between sites with what I suppose people tend to think of as kriging, which is actually just another version of Gaussian process emulation. And it's all described in this paper here in 2008. It's a long time after 2000, which was when the data were, but we didn't actually get them until 2005. It takes an amazing amount of time for people to decide what the temperature was at a certain place in a given year. We don't get the data till 5 years later. Okay. Just brief run through of alternative things you could do. Monte Carlo, you can refine it with things like Latin hypercube, but essentially it's just not efficient enough for the kinds of problems that I want to deal with. If your model is quick enough, blindingly fast, or you've got blindingly many simulators, CPUs to run it on, by all means use Monte Carlo. But you will find a problem that you can't. Sooner or later, you'll need to move to other things. People use other kinds of surrogates, response surfaces, neural nets, other things I mentioned. They all don't behave like an emulator. They all approximate. Most of them are smoothers rather than interpolators. If they interpolate, they don't usually have a measure of uncertainty that says, actually, at the points where I have observed it, I know my uncertainty is 0. The emulator does encapsulate the knowledge that we put into it, and it reproduces it so that when you run it again at the same point, you know what it's going to do. The internal error measures are wrong for these other things as well. That's something I've already mentioned. You do a regression, it misses the points, and it doesn't tell you that you know what the uncertainty is at those points. Okay. I'm a little less unsure about so-called uncertainty quantification methods, which we're going to hear about in the next talk. Polynomial chaos, stochastic collocation, these things. I'm beginning to learn about these things. I think they lack usable internal error measures. I think they're limited in the range of tasks that they can tackle, but as I say, I'm still learning about those things. I want to learn about them because I think that there may be something we can do by combining. Okay. Just quickly, the resources that are available if you want to know the sort of thing we're doing. I'm working with this project called MUCK, Managing Uncertainty in Complex Models. There's its website. We do have an advisory panel with people that provide involvement and help to keep us on track. For instance, Rolls-Royce are on our advisory panel. The methods are being used, not so much by Rolls-Royce, in fact rather a lot more by their competitors Pratt & Whitney. But they are used widely in this sort of area, and they're used by people that are in petrochemical modelling and so on as well. We have this thing called the toolkit, which you'll find from the website. It's a large set of web pages. It's not a set of software tools. It's not intended to be that. We're not at the point where we want to simply give people software and say, go away and use it. People need to understand what they're doing because there's a lot to think about when you're building these things. So a lot of the web pages are about what do you think about, how do you understand what you're doing, and then there are procedures. They are not code, they are sort of pseudocode, but they describe exactly what to do so you can write your own code, and in whatever language you like. There are examples, there are case studies showing how the methods work. We have a mailing list for the community of the to distinguish it from our project, we called it UCM. It's a wider community, Uncertainty in Computer Models. So you can go and find out about the mailing list from this page, sign up to it, and learn from others in the field. We have a conference coming up next year in Sheffield in July. There'll probably be 100, 150 people at that conference, all interested in these problems. There is another one, the SIAM and American Statistical Association are getting together for a conference in April. I think it's also the 2nd or the 4th, but it's April in North Carolina, where we'll try and get together with the UQ community and the UCM community and try and learn from each other. I think that's all I have to say. Yeah. Questions?